Welcome back, fellow mitochondriacs, for another episode of Cancer as a Mitochondrial Metabolic Disease. We are continuing our discussion into ways to essentially diminish or even completely shut down the Warburg effect. And for those of you who are not familiar with the Warburg effect is essentially glycolysis run amok, and glycolysis and huge amounts of excess to essentially fuel a major part of cancer as a whole. And we've been talking about a particular enzyme within that system called hexokinase. And we've been, at least most recently, going through a paper titled The Promoting Role of Hexokinase 2 in Tumor Development. And I would like to continue our discussion into that. Give me 1 second here. Let me share my screen. There we go. Okay. So, like I was saying, we've been kind of diving into this particular paper that was published in December of 2023, titled The Promoting Role of Hexokinase 2 in Tumor Development and Research Progress of Its Inhibitors. And, we had kind of got towards the bottom of the paper, but we kind of ran out of time. So I wanted to give this paper its proper time. And we finished on this part of the paper, which was talking about how there is likely synergistic effects between targeting of glycolysis, or the Warburg effect, and multiple other therapies. For example, in the last talk, we talked about how there was synergistic effects between immunotherapy and how there was an enhancement of immunotherapy, how there was an enhancement of hormonal therapy, whether it be for like ER or PR positive breast cancers or prostate cancers. And now we're at the place of the paper where it's talking about targeting of glycolysis, or in this case, we're talking about hexokinase in particular, to improve photodynamic therapy. And photodynamic therapy is a very interesting therapy. We talked about it pretty much at length right before I hit the methylene blue discussion about how methylene blue could also synergize with photodynamic therapy, in particular red and infrared light photodynamic therapy, given its absorption and strongly about 670 nanometers. But today we're talking about the blockade of glycolysis to improve photodynamic therapy. And, one of the things that I think is very interesting that is, again, not talked about much within the cancer as a metabolic disease topic is how important glycolysis is to maintain redox homeostasis. And there's a couple of like very classic slides that I like to reference when I'm trying to explain this. Okay. So one of the issues with cancer is its management of redox homeostasis. And redox homeostasis is basically the balance of antioxidants and oxidants. And when you have gross amounts of oxidants or reactive oxygen species, reactive nitrogen species compared to the system of antioxidants, then that imbalance can lead to damage and cell death. And so one of the things that cancer is really good at doing is buffering itself with extra antioxidants such as glutathione. So, we talked about this quite a bit when we were going through the glutaminergic pathways, because we were talking about how glutamine is converted to glutamate, and then glutamate is one of the 3 amino acids that make up glutathione. And we also talked in particular about how, because so much glutamine is being brought into the cell, that it's even able to sacrifice some of the glutamine to bring in cysteine. And that antiporter was called XC or SLC7811. And we saw that there was a paper even titled that the SLC7811, that antiporter that brings in cysteine to help build glutathione with the help of glutamate, or the glutamate in that case, is one of the Achilles heels of cancer. Because when cancer cannot make enough glutathione, we focus a lot on the energy production part of it, the ATP production part of it, but this is also very important. And so we kind of really hit this pretty hard from the glutamine side of things. But what we did not hit from very hard was the need for glucose to also maintain redox homeostasis. And you'll see glucose is here, and it gets converted by hexokinase, the enzyme we're talking about in this particular paper, or in this particular series of videos. And that is going to convert glucose that gets uptake by the cell to glucose 6-phosphate. Glucose 6-phosphate can participate in the PPP, or the pentose phosphate pathway, to help recycle NADPH. NADPH is what helps recycle glutathione. And so therefore, there's also a need for glucose as part of the antioxidant system to recycle glutathione and to make it more resistant to oxidative stress. Just another graphic that I've been using ever since it was recently published was this paper by Seafried. And this graphic is beautiful because it shows glutamine is contributing to glutathione, okay? But also glucose is contributing to glutathione in two different ways. It's talking about here by the creation of glycine from glucose, but it's also, what it's not showing here is the PPP making the NADPH, which also contributes to glutathione. And it requires both to effectively make glutathione in high quantities to be able to withstand the excess oxidative stress that is known to be within cancer cells. Now, imagine we're now back to glucose, talking about photodynamic therapy. And if anybody remembers what photodynamic therapy is actually doing, it's basically another version of an oxidative stressor that the normal cells can handle, but the cancer cells effectively cannot. And so it would make sense that the blocking of glycolysis, or the blocking of hexokinase in this particular case, would improve photodynamic therapy, because it's going to be hampering the cancer cell's ability to recycle glutathione and protect itself against oxidative stress. So let's see what it says here in this verbiage of this paper. It says, photodynamic therapy is a relatively new, minimally invasive therapeutic procedure that relies on selective accumulation of a photosensitive compound in the cancer cells, which, on excitation with light of an appropriate wavelength, would generate ROS, reactive oxygen species, or oxidative stress, predominantly singlet oxygen, within the cancer cells, and eventually kill the cancer cell with minimal damage to the surrounding tissue or the normal cells. Although PDT, or photodynamic therapy, is widely used to treat several cancers, its efficacy is limited by several factors, including the effective irradiation of deep tissue. We've talked about that kind of at length with the use of red and infrared light, how that kind of negates at least part of that argument. Therefore, several studies have attempted to improve the efficacy of PDT by combining with other chemotherapeutic agents. It has been shown that glycolytic inhibitors disrupt cell metabolism, elevate the cellular ROS, and disrupt the mitochondria, resulting in cell death. Therefore, when combined with PDT, glycolytic inhibitors could, in theory, enhance the levels of ROS and thus trigger increased cancer cell death. I just want to highlight something here that I think is important, and I've highlighted it multiple times in the past, but it says here that it disrupts the mitochondria. What is it effectively doing? When we create reactive oxygen species that damage the mitochondria terminally, the mitochondria will release proteins, in particular cytochrome C, to the rest of the cell, which will basically trigger apoptosis. So that's what it's talking about there. In another study, an 18-hour glucose deprivation prior to PDT reduced intracellular glutathione levels and increased the cytotoxicity of PDT. A similar increase in PDT efficacy was observed when inhibitors of glutathione synthesis, this buthanone sulfoxamine, or its regeneration by the other chemical, were used for co-treatment with PDT or photodynamic therapy. Changes in the availability of glycolytic substrates affect NADPH availability in the cells, exactly what we just talked about in that graph. NADPH is a critical agent involved in the antioxidant defense mechanism of the cell. As mentioned, PDT relies on increased ROS in the cancer cells to kill them. PDT-based ROS generation under conditions of impaired glucose and glutathione metabolism results in much higher intracellular ROS levels, contributing to increased efficacy. In line with this, the ROS scavengers were shown to protect the cells from ALA PDT-induced damage. I'm not sure what ALA stands for in this case. I think they were using maybe alpha-lipoic acid as a photosensitive molecule. I'm not completely certain about that. I'll have to look again at that paper. A recent study showed that the metabolic reprogramming towards aerobic glycolysis, or the Warburg effect in cancer, contributes to the development of resistance to 5-ALA. Maybe it's something else. It could be I think there's another photosensitive molecule that's called 5-ALA, which makes it a little bit more clear. But I'm going to get back to you on that. Further, they showed that treatment with metformin reduced glycolytic or aerobic glycolysis and increased OXPHOS in squamous cell carcinoma cells and improved the cytotoxic effects of PDT by increasing PP9 production, ROS generation, and AMP kinase expression, and inhibiting AKT-mTOR pathway. In another study combining a glycolysis inhibitor, 2DG, with 5-ALA induced an enhanced accumulation of this PP9 in these HepG2 liver cancer cells, contributing to the improved efficacy. Further, treatment with 2DG and bromopyruvate synergistically improve the efficacy of photodynamic therapy in breast cancer cells. So we're going to have an entire video, maybe even more than one video, on 2DG. Okay, 2DG is a coming attraction, but no matter what, we have to discuss it a little bit this second, just because this paper is talking about multiple hexokinase inhibitors, one of which being metformin, and one of which being 2DG. So let's go to, let's see here. Should I use this graphic, or maybe I should use this one? So, a couple of things. This paper is talking about there's three different modalities that are being used in that very small blurb of text. Okay. Number one, they improved efficacy of photodynamic therapy using just a fast of 18 hours, right? So basically, the glucose that would normally be abundant in the extracellular space is less. So therefore, there's just less available to metabolize into lactate and, use aerobic glycolysis. Okay. That showed efficacy of PDT, because when we restrict glucose, we now have a problem at making antioxidant systems work, and therefore the extra reactive oxygen species within the cancer cells are diminished and exploited by PDT. The other thing that they used was 2DG, 2-deoxyglucose. Basically, we're going to talk about this at length, but 2-deoxyglucose is glucose with an alcohol or an OH molecule at a different position, and it's removed, excuse me. And what essentially is happening is that it is fooling the hexokinase 2 enzyme, and it basically cannot proceed with metabolizing glucose that's normal. And that will basically block this and effectively shut down, to some degree, the Warburg effect or aerobic glycolysis, or the amount of sugar that's able to be metabolized under normal cancer physiologic conditions. And then what's happening is, because that sugar is diminished and the ATP is diminished and the lactate is diminished, and because all the other stuff that goes along with blocking glucose from being utilized by these cancer cells, one of the things that's diminished also is the ROS buffering capacity, or the cancer cells' ability to manage redox homeostasis within their own internal environment. And then we're hitting it with some photosensitive molecule, this 5-ALA in this case, and this talking about this paper, and the wavelength of light, which I believe is going to be either purple or blue. Again, we're going to look at that again. It could be way off base there. I'm trying to remember back from the photodynamic therapy paper or videos that we did. And they're having a pronounced effect, which makes a ton of sense. So basically, the conclusion is of this paper, which I thought, this paper was excellent at making our points about how important just one enzyme, just hexokinase, imagine how that underscores our points to metabolic therapy as a whole, how that underscores our importance to keto or fasting or other things, right? But we're looking at hexokinase in particular with this paper. And it's an excellent paper at the kind of the entire landscape of how it could be exploited to enhance the standard of care and these kind of emerging therapies such as photodynamic therapy. So in the conclusion, it says elevated glucose metabolism, hypoxia, induced GLUT transporters, lactate dehydrogenase, phosphofructokinase, overexpression, and the AKT c-Myc mediated transcription activation of hexokinase 2 are observed in most cancer cells. And these metabolic changes may be exploited for developing effective therapeutic approaches. It later says that elevated glucose metabolism and nutrient uptake have been exploited for tumor diagnosis in the clinic. The F18 fluoro 2-deoxyglucose PET, or this PET scan, is used widely in the clinical staging of cancers. However, glycolysis inhibition has not been fully exploited to its full potential in cancer therapy and is not translated in the clinic. So you may be able to argue that in research that it's been exploited, or it's been attempted to be exploited to some degree. But in clinical medicine, it's not exploited whatsoever at all, other than with a PET scan. The same doctor that orders the PET scan and utilizes this particular process happening in cancer cells will then tell you that diet has nothing to do with cancer, glucose doesn't rely on cancer, et cetera, ignorantly, frankly. So this is the big jump, right? It's taking what has been known since the time of Otto Warburg and taking that and putting that into the actual hands of clinicians and building protocols. And that's what's hopefully happening to some degree right now. I would say it's not happening near fast enough, or maybe not at all, from what I'm seeing, from my perspective. Later it says, despite early indications, glycolytic inhibitors such as 2DG have failed in clinical settings due to their limited effects as a monotherapy agent. Again, this is mainstream medicine one pill for the ill, right? Like, I don't believe that anyone, even the most amazing substances that I believe are unbelievable, will ever work in a vacuum. It's never going to be a monotherapy. And you can't then, reason that, because 2DG failed in clinical trials as a mono agent, then it's useless. That is like third grade level thinking. And we're going to, put our thinking caps on and be like, okay, we can see how this could be used as a tool. Anyway, I'll digress. In addition, it might be necessary to combine glycolytic inhibitors with other agents that target alternate pathways that are activated in response to glycolytic inhibition. Studies have shown promising effects with metformin that inhibits mitochondrial complex 1, which is why I don't like it for preventive medicine, but that's what it does. At least one of the things that it does was used along with glycolytic inhibitors. But as we have talked about in this particular paper, that metformin by itself blocks hexokinase, similar to 2-DG. So it is a glycolytic inhibitor. Using glycolytic inhibitors as adjuvant therapy with already approved conventional therapies, including chemotherapy, radiotherapy, immunotherapy, and photodynamic therapy, is an attractive strategy. And several early studies have shown promising results. Dietary interventions and lifestyle changes also affect the metabolic landscape of cancer cells, and studies should address this issue in detail to emphasize their clinical implications. So you see how it says that glycolytic inhibitors, and then later on that lifestyle and dietary intervention should be adjuvant therapies? No. What should be adjuvant therapies would be chemo, radiation, and immunotherapy, maybe photodynamic therapy, but I find that photodynamic therapy probably makes a lot more sense to be part of the standard of care, along with glycolytic inhibitors, glutaminergic inhibitors, and dietary interventions as the first line. And then if you, God forbid, have to use an adjuvant therapy, then use things that are less safe for the normal cells, right? Like chemo and radiation therapies. Again, that's this particular individual's opinion about how things should go. But again, this is a little bit in contrast to what the authors of this paper are showing. So I wanted to next hit, I'll be very frank with you guys. I had no idea that metformin blocked hexokinase until I started reading these papers. I knew that there was going to be benefits to metformin. We talked about metformin in a standalone video, in particular talking about its effects on glutamine metabolism. I think there's a lot of different ways you can talk about metformin. Not only the blood glucose side of things, which is going to enhance metabolic therapy, its effects on AMPK, etc. But what I would also say is that I am now aware of it being a hexokinase inhibitor. And I thought, wow, this must be new science. And it's not. As a matter of fact, I found this paper from 2013 in Cell Cycle that is titled Direct Inhibition of Hexokinase Activity by Metformin at least partially impairs glucose metabolism and tumor growth in experimental breast cancers. So this just goes to show that even, how do I say this? As you can imagine, by looking at the videos that I published to date, and we're about a year into this journey of looking at cancers and metabolic disease. That's when I started this I had been on YouTube for quite a while, but I had not published videos in any regular fashion until about April of last year. And I think we've made a lot of headway. I know I've made a lot of personal headway. I've improved my understanding of cancer exponentially. And the reason why I've been able to do that is because I am, as you can imagine, by looking at my slides, I'm in the literature continuously. And I have a love for learning. And what I'm saying is that the literature is so vast that even when you're looking for the answers, they don't come up until later on. And that's why I appreciate, all of you guys, because there are people who are emailing me, sometimes continuously, or at least giving me comments that give me clues to other things that I missed. Even when I'm directly searching for things, I'll miss it. And some of you will pick up the slack and help me out. And I'll be able to, pull that paper or that reference or whatnot and add it to our understanding of all of this. And I just think it's interesting because I've done a lot of literature searches on metformin in particular with cancer, and I was unaware of its inhibition effects on hexokinase up until about maybe 2 weeks ago, maybe 3, which seems kind of like a very short amount of time considering how deep and much I've been into the literature the last several years. So with all that, I'll digress. It says here that emerging evidence suggests that metformin is a widely used antidiabetic drug, may be useful in the prevention and treatment of different cancers from a variety of aspects. Let's not forget. In the present study, we demonstrate that metformin directly inhibits the enzyme function of hexokinase 1 and 2 in cell lines of triple-negative breast cancer. Measurements of the 18F fluorodeoxyglucose uptake, or PET scans, document that it is a dose and time-dependent and powerful enough to virtually abolish glucose consumption despite unchanged availability of membrane glucose transporters. The profound energetic imbalance activates phosphorylation and is subsequently followed by cell death. Administration of high drug doses after tumor development cause an evident tumor necrosis or uncontrolled cell death in a time as short as 48 hours. On the other hand, 1 month metformin treatment markedly reduced cancer glucose consumption and growth. Taken together, our results strongly suggest that HK, or hexokinase inhibition, contributes to metformin therapeutic and preventive potential in breast cancer. I'll just say it, probably all cancer, because again, the upregulation of glucose utilization, aerobic glycolysis, Warburg metabolism is a hallmark of cancer. So therefore, although they're studying it on this triple negative breast cancer model, very likely able to be extrapolated to all other cancers. I just think it's fascinating that despite these cancer cells in this particular study upregulating the glucose transporters that we talked about in the last couple of videos, which are also important, metformin in a dose and time-dependent manner was powerful enough to virtually abolish glucose consumption. I mean, that's pretty unbelievable. This goes to show how important hexokinase is. Hexokinase is a rate-limiting enzyme step within glycolysis system. So if you're shutting that down, it doesn't really matter how much glucose is being brought in, according to this particular, work that was done in 2013. And I just think it's fascinating that something as fairly safe and cheap as metformin is not being part of the standard of care with a paper is kind of exciting as this in the world of, metabolic cancer treatment. I would say that I'll reiterate that I'm not a huge fan of metformin for preventive medicine, just because I'm a mitochondriac and I want to maximize mitochondrial, efficacy, and blocking complex 1 is not a huge fan of mine. But that being said, I think that kind of like I'm not a huge fan of statins either, but for a very defined goal and specific purpose and limited amount of time, right? Not forever, but for a limited amount of time, I think that some of these, pharmaceuticals are pretty compelling, and they're being in their use for cancer. Again, like it said in this paper here, what was it? The 2DG said it was kind of brushed aside because it wasn't effective as a monotherapy. Metformin will not be a monotherapy. Statins will not be a monotherapy. 2DG will not be a monotherapy. DON will not be a monotherapy. Keto will not be a monotherapy. Okay. It's when we, and I want to hammer this point home. It's when we, as this beautiful Seafried slide suggests, it's when we hit glucose at likely multiple levels, fasting, keto, lowering glucose with exercise, cold, photodynamic photobiomodulation, et cetera, supplements, drugs, lowering blood glucose availability, potentially blocking glucose transporters, potentially blocking glycolysis at multiple levels. In this case, we're talking about hexokinase, right? In addition, a therapeutic ketogenic diet, which is fairly low in protein, not like deficient in protein, but fairly low, potentially blocking multiple glutamine transporters, the glutamine machinery, glutamine dehydrogenase, glutaminase, et cetera, other antiporters such as SLC711. We are essentially shutting this whole entire process down. Now we're looking at one very small part, hexokinase, and we're seeing how powerful that could be and enhancing the standard of care. So shutting these processes down this is the Achilles heel number one, left and right, of cancer. All the mechanisms that it is able to affect are, biochemical discussions that we've had over the last year, essentially. But glucose and glutamine, not a monotherapy, is going to be the ticket. And I would even say not even glucose and glutamine is probably enough. That is probably an argument and discussion for another day that I hope to have with some people that are big into this literature and publications, such as the man himself, Seyfried. I hope to have that discussion with him. But even him in the 2017 paper, what did he say? Oxidative bomb. In that case, he was talking about HBOT. I think there could be multiple arguments for multiple different oxidative bombs, such as photodynamic therapy, like we talked about in that most recent paper. It could be IV vitamin C. It could be potentially ozone, many different things. But ultimately, that's how it works. It works in synergy, and it needs to be a three-legged approach: glucose, glutamine, and oxidative stress, in my opinion. But I think that this literature really helps us get closer to the real answers about how to attack this problem. And I think that it's pretty much found in this text here talking about targeting glycolysis to improve photodynamic therapy. I think it's also found here when they were talking about using DAWN to improve anti-cancer tumor immunity, which is kind of a paradoxical thought. We thought that, or at least a lot of people thought that if you inhibited glutamine, you were going to inhibit the immune system's ability to kill cancer cells. And now with multiple publications, that seems to be maybe not true, which is why I personally believe that glutamine inhibitors probably don't need to be pulsed, although that I think could be arguable. But I think we're getting closer and closer to the answers with every single publication kind of like hammering these key points. The next paper I wanted to hit on was a very interesting paper that talks about metformin again, but metformin not in a vacuum, which I like. And it said it's a more recent paper. It's in June of 2022, and it's titled "Tumor Metabolism Destruction via Metformin-Based Glycolysis Inhibition and Glucose Oxidase-Mediated Glucose Deprivation for Enhanced Cancer Therapy." And I'm going to read some of the abstract, some of the paper, and there's some really cool graphics associated with this. So it says cancer cells rely on glucose or glycolysis to support a high proliferation rate. At this point, I don't know how many times I have to hammer that point home to our audience. I think we know that at this point. But that being said, metformin is a promising drug for tumor treatment that targets hexokinase 2 to block the glycolytic process, therefore further disrupting the metabolism of cancer cells. It later says the liberated metformin blocks the glycolysis process via suppressing the activity of hexokinase 2 and impairing ATP production, much more than that, but ATP production, which activates the AMP, activated protein kinase AMPK pathway, and P53 pathway, and damages the Warburg effect, eventually leading to apoptosis. According to the in vitro and in vivo assays, the combination of glycolysis inhibition and starvation therapy, aka fasting or ketogenic diet, okay, I like that. I like where this is going, demonstrates efficient cancer cell growth suppression and superior anti-tumor properties compared to metformin-based or glucose oxidase mediated monotherapies. So you're telling me that if I go on a ketogenic diet or I fast and I do metformin, it's better than just doing it by itself? Yes. Well, that would be obvious, I think, to most of us here. This work provides an advanced therapeutic strategy via disrupting cellular metabolism against cancer. So, well, let me get into it. Oh, so I'm sorry. This is the paper that was like the concept. And then the more recent paper was this one, sorry, March of 2024, enhancing metformin-induced tumor metabolism destruction by glucose oxidase for triple combination therapy. Let me go back quickly here first. So Metformin, I think most people on this channel probably have a clue or have heard about it at least, and kind of like understand where we're using metformin based off of the most recent, you know, paper that I just talked about, but also prior um, videos that I've published about its effects on the metabolism of glutamine and the building of glutathione. So my point is that I think the glucose and glutamine and metformin part of it we are on board with. Okay. That being said, this is a new player. This glucose oxidase is another interesting thing that's being used in this paper and the subsequent papers, which is why I want to kind of cover it. Okay. So glucose oxidase essentially breaks down glucose so it can't be used in metabolism. And that's why it's being kind of like a synergistic therapy for metformin. And it's kind of like simulating being on a fasting or a ketogenic diet. I'm guessing. I'm guessing what they want is they want a pill for this problem and not you to change your lifestyle, unfortunately. You know, again, ketogenic metabolic therapy should be the standard of care. It should be the baseline foundation, but that requires, frankly, it requires effort. It requires tracking. It's not easy. And so they want like a kind of a pill solution to this. So I think that's why they're going for the glucose oxidase, kind of like, nanoparticles or whatever they're using here. And they're using in the next paper as well as a way to kind of do this, in, I don't want to say less painful, but in a drive-through answer. Let's be honest, So, and they want to develop drugs, of course. So my point is, I just want to at least touch on this glucose oxidase. These other papers may also touch on it. So enhancing metformin-induced tumor metabolism destruction by glucose oxidase for triple combination therapy. Despite decades of laboratory and clinical trials, breast cancer remains the main cause of cancer-related burden in women. Let that sink in. We have all these other therapies, and it still remains the main cause of cancer-related burden. So number one, that means that we're not preventing it. Number one. Number two, we have not made, drastic improvements in the way we are attacking the problem. So therefore, we're having it still being the main cause of cancer-related burden in women. Considering the metabolism destruction effect of metformin and cancer cell starvation induced by glucose oxidase, after their efficient delivery to the tumor sites, glucose oxidase and metformin may consume a large amount of glucose and provide sufficient hydrogen peroxide in situ. Herein, the pH-responsive EGCG conjugated low molecular weight chitosan nanoparticle were constructed. So basically, they made a nanoparticle, this like thing here, that has EGCG, chitosan, metformin, and glucose oxidase. Again, they're trying to like take what probably could be done by most people at home with Amazon and your doctor's prescription of metformin and a ketogenic diet and package it in a way that they can probably sell for billions of dollars. But my point is that they're using a combination at least, okay? And I at least like that. The coordination between iron ions Fe3+ and EGCG in this nano platform can enhance the efficacy of chemodynamic therapy via the Fenton reaction. So what they're saying is that these three things by itself, in addition to iron, can enhance the Fenton reaction and lead to cancer cell death, which is the same way that IV vitamin C or many of these oxidative therapies work. That's ferroptosis, right? Ferroptosis is using iron with oxidative stress to kill cancer cells. It later says that the in vivo anti-cancer results indicated that this metabolism destruction / starvation / chemodynamic triple combination therapy could increase apoptosis / death of tumor cells and reduce their proliferation. The triple combination therapy approach is promising for efficient and targeted cancer therapy. So look, I'm glad in some ways that pharma and industry is basically proving the point that Dr. Seyfried put out years and years ago in his book and subsequent mini papers, right? You know, basically shutting down metabolism plus oxidative stress, right, is an effective approach and promising approach, an efficient approach at targeting cancer treatments. And this is a very, fairly new paper, March of 2024, correct? So let's kind of like look at some of the cool graphics we have here that are associated with this paper. So again, we have multiple interventions packaged in one nanoparticle that gets to the cancer cells, unloads its payload, right? It's going to destroy the glucose with the glucose oxidase. It's going to, block metabolism in multiple ways from metformin, and that's going to lead to decreased glucose availability, decreased ATP production. It's not really shown here directly, but there's going to be an increased reactive oxygen species because of, yes, glucose is, because of the generation of hydrogen peroxide, but also the fact that glucose cannot be used to recycle glutathione. It's going to talk about EGCG being, important to liberate iron and make it more kind of available for the Fenton reaction to happen. And you got this kind of like beautiful synergistic thing going on. We got starvation therapy, we got metabolism disruption, we got chemodynamic therapy, they're calling it. And we ultimately end up with cell death of these tumor cells. This is another graphic of the paper that is kind of more zoomed in, just the same graphic, just more zoomed in. So anyway, I thought this was a really kind of very frustrating paper because, again, we're like stacking up W's with these papers, right? They're like showing what Seyfried and others have been doing is very likely going to work, right? And it makes biologic sense. It's just that they want to repackage that idea, right, into something they can make money with, which I get, and maybe makes it more effective. I don't want to be so pessimistic about this. It's just that it just is, but it's also at the same time like kind of validating us that we're on the right track here, right? All right. So we've talked about some kind of like a couple of the unnatural glycolysis inhibitors or hexokinase 2 inhibitors, but there are a bunch of, natural hexokinase 2 inhibitors as well. And one of the first papers I published was from this phytotherapia. I'm guessing it's an international journal here, and it's titled "The Natural Inhibitors of Hexokinase 2 Steroids from Ganoderma sinensis." And we're going to talk about that a little bit, but that is I believe I had to look it up. It was the purple reishi mushroom. So, I had planned on talking about, the medicinal mushrooms kind of after we hit metabolism, but come to find out that at least from a glucose standpoint, reishi mushroom has an effect at blocking hexokinase. So hexokinase 2, a rate-limiting enzyme and the first step of the glycolysis pathway, expresses at high levels in cancer compared to normal cells because of the Warburg effect. HK2 provides a new target for cancer therapy due to its pivotal role in tumorigenic and metastatic process. The structure-based virtual ligand screening in a small in-house database of natural products predicted that a new steroid, which I'm not going to even attempt to try to pronounce because it is about 10 words long, from this Ganoderma sinensis, which is again purple reishi, has high binding affinity to hexokinase 2 with significant calculated binding free energy. And compound 2 was finally identified as a hexokinase 2 inhibitor as the first natural hexokinase inhibitor. Compound 2 can be considered a potent drug candidate targeting at HK2 for cancer therapy. I don't know if that's necessarily true. That's the first HK2 inhibitor that's natural. I mean, because I'm going to pull a bunch, and I have to imagine that they've known about those for a while. But anyway, the bottom line is that there are a whole host. This kind of is my segue into showing that there's a whole host of natural inhibitors as well. I like to give those. And then the next paper, which was published in 2022, that is titled Identification of Plant-Based Hexokinase 2 Inhibitors Combining Molecular Docking and Dynamic Simulation Studies. It says cancer cells ferment glucose even under aerobic conditions. Following a phenomenon known as the Warburg effect, hexokinase 2 catalyzes the crucial step of phosphorylation of glucose and subsequent utilization in glycolysis and other pathways. Hexokinase 2 has been proposed as a potential therapeutic target for anti-cancer therapy because of its enhanced expression in glucose-dependent tumors. It later says that finally we have identified that EGCG and quercetin, two natural compounds with appreciable binding affinity and efficiency and specificity towards the HK2 binding pocket. Both compounds were found to be binding preferentially to the HK2 active site and showed a decent set of drug-like properties. So, this is a more recent paper, but I thought that it was interesting because it's saying that EGCG and quercetin are some of the most effective HK2 inhibitors that were identified when they were studying like multiple small molecules and natural compounds. And it just goes to show that, EGCG and quercetin are probably two of my favorite really molecules that have been studied for, plant medicine, basically, because it has such diverse effects on cancer as a whole. So, which leads me to this slide here, which is my current kind of gestalt slide for looking at the blockade or inhibition of hexokinase 2. And very similar to the, other pathways that are blocked, you'll see a lot of these over and over again. And I don't know if that's because they're just more popular than other kind of like natural compounds and they just get studied like, okay, we figured out that, sulforaphane blocks, this. Should we look at it and see if it blocks this too? And there's money that goes into it. I'm not exactly sure why, or if these are just truly the kind of like really the heavy hitters within the, natural products. But anyway, we're going to see that EGCG, sulforaphane, artemisinin, capsaicin, luteolin, resveratrol, curcumin, quercetin, vitamin D are all kind of like seen over and over again in a variety of metabolic pathways. Some of the ones that are not as commonly seen, but we did see it in the last one. As a matter of fact, let me pull that up really quickly since I have it at my fingertips here. This alpha heterin, that was seen in the gluten inhibitors. This genistein, was one of the most powerful glucose transport inhibitors at multiple different transport inhibitors, right? As well as apigenin, right? Apigenin, which is something I haven't really talked about much on the channel so far, but those are two of the most potent GLUT transport inhibitors. And then when we go down to the natural hexokinase inhibitors, you're going to see apigenin and alpha heterin and genistein again, right? So these compounds, even though they have diverse effects on one particular target, they also have multiple targets that they have, effect upon. And as it said in this most recent paper that I was pulling from, this 2022 paper, quercetin and EGCG have basically drug-like properties. I mean, what they mean by that is that they have very high affinity to these particular, they don't just like hit it a little bit. They hit it like a hammer. So again, EGCG, gosh, man, EGCG is just unbelievable. So is quercetin. Quercetin is probably my favorite, although it's hard to really rank them at this point because they have so many diverse effects. I mean, then I'd be skipping out on curcumin and artemisinin and all the other stuff. So my point is, this is my current gestalt slide for the inhibition of hexokinase 2. I want to say that someone in the comments just a couple of days ago told me about rhodiola rosea, which I also use clinically for other things, and I haven't really seen it pop up much for cancer much when looking at it from a metabolic perspective. But I think I think that person told me either blocks glucose transporters or hexokinase 2. So I may have to add that onto this Gestalt slide. But I mean, the bottom line is you have a ton of tools in your tool bag, okay? Just for this particular enzyme in particular, this hexokinase 2. Obviously, we have multiple natural things as well as multiple, drug-like things. I think someone in the comments here, let me see here. So Michael's talking about water fasting. Michael, you had put a bunch of comments kind of about the same thing about water fasting. I want to cover it. I don't know when I'll cover it, but I do want to cover it. Okay. Just want to reiterate that. Let's see here. Do my first metformin in 5 minutes. Good job, Alan. Let's see here. Can PDT be effectively used for brain cancer? That is a discussion that I'll try to touch on. Hi, Doc. Cover. So this is the one I wanted to cover. I saw this in the background and I wanted to. So 3-bromopyruvate is going to affect the hexokinase 2 enzyme. It may have another place where it affects. I may be wrong. For some reason, I thought it had another part of the process that hit. I think it also maybe blocks the phosphofructokinase enzyme as well. Anyway, we'll hit it when we hit that enzyme in particular. I don't know. I mean, 3-bromopyruvate, we may have to do a video on it. We'll see. I don't know if it'll be a full video or if it'll just be kind of like part of, one of these larger Gestalt videos about a particular subject or not. But we may. Ray, nuggets from my existing specific tools, specific times. That's right. So many tools, mostly ignored. Yeah, almost exclusively ignored by the paradigm, Ray. Closer and closer to synergy. Yeah. I mean, I think that, again, I'm going to reiterate. I think that when it's all said and done, prevention is the best medicine, right? So not getting a disease in the first place. But what I'll say is that it's going to be the answer to treatment will likely be a synergistic kind of approach. Does that to be exactly what Seyfried and et al. Has talked about? I think that is a beautiful illustration of what is possible and what is likely to be a foundational approach. But to be very fair, I think that there's a lot more that one can do than what is just published in the in those kind of in the Seyfried papers, and therefore I believe that it's going to expand and hopefully rapidly and exponentially expand to a lot more things. I think the issue that I and clients of mine have is that you see a list like this, right, and you're like, oh my God, I want to be on all this stuff. And, when you look at all that stuff and you look at it being, let's say, a supplement of EGCG and sulforaphane and artemisinin, before you know it, in order to get like therapeutic dosage of these things, like you're taking like 20 pills a day and you're coughing up, powders from pills, And so I think the issue is that the delivery system has got to be worked out. Like if someone in industry could like make me a powder that has therapeutic doses, the good versions of these supplements in a drink mix that that would could blend into like a smoothie or something like that, that didn't taste god awful. That would be a step in the right direction with a lot of this stuff. So you're not taking so many pills per day, but there's just a lot, that's not even just the end of it. It's also about like absorption in the system. A lot of these compounds don't absorb well. So therefore, like we need to look at like what we call parenteral routes, like, using like intramuscular, subcutaneous, intravenous injections of these things potentially, and then having those things available. I know that I've seen in my short time, in this world, I've seen intravenous EGCG. I've seen intravenous, I believe, artemisinin, I think can be intravenous. I've seen intravenous curcumin. I've seen intravenous quercetin. I don't think there's any real reason to have intravenous, vitamin D. But some of these other things, I would also, well, I guess I'll probably talk about it when we talk about the 2DG in general, but there's kind of like some route of administration issues with that as well. So my point is that it's not just about the route of administration. It's not just about like formulations that minimize, the amount of pills a person's taking per day, therapeutic dosages, et cetera, timing, et cetera. I think needs to be worked out. But hopefully with, this becoming more and more, God willing, I don't want to say in vogue, because it's not going to be a fad. This is going to be, God willing, the standard of care. Hopefully this becomes more and more kind of entrenched within the research community. Clinicians like myself and others will start to, use these tools at our tool bag and start to enhance the standard of care. And then hopefully at some point this will become the standard of care. And then once it's the standard of care, then hopefully industry, or maybe not industry, but maybe government, can fund studies that can get us the protocols we need to, or the routes of administration we need to, enhance the therapies, enhance the protocols, perfect the protocols, and we can have a really good system, at some point. But we're so far from that. It's kind of sickening. Let me take a look at some of these. So, Ray, you asked a good question. How well do mitochondria recover from anesthetic hits to complex 1? That's a great question. I would say that if you look at, Dr. Cruz's perspective, if you're utilizing mostly fat for fuel, you're going to bypass, I believe, complex 1 to some degree because of the ratio of NADH and FADH2 that's made by fat for fuel versus carbohydrates for fuel. Dr. Cruz talks a lot about like complex 1 being activated by purple light, because it is going to be activated when UV is out, which would be summer months, or, being in tropical climates and being able to, eat more carbohydrates. I will leave the details of that to him, because he's just up there, when it comes to stuff like that. What I would say is I would just say, look, it's not ideal. Blocking complex 1 is not ideal for the normal cells, which is why I'm not a huge fan of recommending it for preventive medicine. I do think that for a targeted amount of time, for a very defined purpose, such as killing cancer cells, I think it would be a small price to pay, but time will tell with that. What about restoring gut microbiome? So, I would say that for me, from what I understand, it's probably not. Let me back up a second. So again, one of the issues that we have within metabolic therapy, or maybe that I have, I don't know, but I would say it's kind of a systemic issue, because when people come to me who've never met me before and they do a consult, they're on 50 different things, right? So the issue is that when we're trying to attack cancer from a metabolic perspective, we're already dealing with like multiple things that we're on. So, and we know that the blockade of glucose and glutamine are the most important things, and then hitting it with an oxidative stressor is like the trifecta, right? So my point is that although I do believe that restoring the gut microbiome is important, do I believe that it's critical? I don't think it's critical in the short term. Could it be critical on a case-by-case basis, depending on your kind of like N=1? I think it could be. If you have been given antibiotics 15 times and you have like opportunistic infections and like, diarrheal illnesses and C. diff, colitis, colitis and stuff like that, and you're like hospitalized all the time, then I think that, the restoration of your gut microbiome now, like maybe, number 1 on your list, because if you, die of septic shock from C. diff, colitis, or toxic megacolon, then what's the point of doing metabolic therapy for cancer, right? So it's going to be an N=1 scenario. I think for most people who don't have that kind of extreme example of a clinical scenario, I think that probably it's lower in the list of things. Now, that being said, I will make a quick digression. How do a lot of these phytonutrients and fibers work to lower blood glucose and lower inflammation and et cetera, et cetera? They work at modulating the microbiome. So, in some ways, if I put you on EGCG or sulforaphane or resveratrol or curcumin or quercetin or whatever, I am affecting your microbiome, right? Without directly giving you like probiotics or prebiotics, right? Although I would argue that a lot of these resveratrols and different, phytochemicals are prebiotics. So in some ways, we are restoring the microbiome without maybe having a microbiome, centered thought process behind why we're doing these things. I hope that makes sense. All right, guys, we've got an hour. I was expecting to go a half hour today because we didn't have many slides to get through. And here we are, another hour in, and I'm very surprised, but it is what it is. I'm happy to be with you today to share this information. If you like videos like this, please like, share, and subscribe. We have a lot more to share. The next video or two will be on probably 2-deoxyglucose or 2DG. And then I'll probably go to the next enzymatic step in the process, probably phosphofructokinase. But if I can find another intermediate step that is high yield for us to, focus on, to look at, we'll hit it. So until next time.